All right, guys, in this lesson we're going to be looking at parameters for regression slope, and our objective here is just to check the conditions for performing inference about the slope of the regression line, and we're going to interpret the values associated with the regression in context. So if you kind of think back a couple chapters ago, you remember that we took a sample, basically, just a sample, and we're taking a sample to try and make an inference or a prediction about a particular population. And so let's say that we made a dot plot just like this, and each one of those dots represented a particular result in that sample, and we're checking between two specific variables, basically, that we're trying to see if there's an association between those. And if that made kind of a linear form, if all of those samples combined made some kind of linear form, then we could say that that there was a similarity between the sample and the population as a whole. And then if we were to draw a line right through all of those samples, then that's what was known as our least squares regression line. So essentially what we're going to do with this chapter is we're going to kind of combine this idea of what a least squares regression line actually represents and what we've kind of been learning for the last couple chapters. So again, we take a sample to try and make a prediction about a particular population. And so just like the sample has its own progression line, we also have a population regression line as well. And so the population regression line is the line that best reflects the value of a response variable given the value of an explanatory variable in a population of values. So basically, if we take a whole bunch of samples and we combine them all together to create what we know about the population as a whole, that population is also going to have its own regression line. Whereas a sample regression line is basically the exact same thing, but it's the line that best reflects the value of a response variable given the value of an explanatory variable from a sample taken from a population as a whole. So when we're looking at that image that I just showed you, we think about this example. How long would you wait for the next eruption of Old Faithful if you know how long it erupted? So let's say that this image right up here represents as a scatter plot of the duration and interval between eruptions of Old Faithful for all 222 eruptions in a single month. The population least squares line is shown in blue. So all of these little dots represents how long that eruption actually lasted, as well as how long in between each one of those eruptions actually lasted out of, and each one represents one of the 100 or the 222 eruptions in a single month. Now, let's say that we wanted to go a little deeper than that. Let's say that we didn't want to take all 222 eruptions in a single month to figure out if there was some kind of correlation between those two variables. We just wanted to take a sample of about 20. And so let's say that each one of these graphs represents just simple random samples of 20 Old Faithful eruptions. And so what we want to do is we want to take 20 Old Faithful eruptions and we want to see, if it comes close to what we got in our population of just a whole month's worth of 222 eruptions. Well, what you're going to notice, or what you should notice, is what you see right down here below, and that's our least squares regression line, our sample regression line for each one of these particular samples. And you'll notice that they're all different, okay? They all have different intercepts, they all have different slopes, they're just different. And so our point here is that each one of these samples is not going to equal a particular population, but the particular population regression line that we're actually looking at. But what we want to try to infer is how can we combine each one of these regression lines so that it makes up, or it comes to a conclusion that is extremely close to the actual population regression line that it's trying to represent, basically. So that's kind of the goal, or the idea behind this this regression idea. But what we want to do before we do any of that is we want to describe our sampling distribution. And so again, to describe our sampling distribution of a regression slope, we must discuss the shape, center, and spread of that regression slope. So we are looking for a sampling distribution for a slope that is approximately normal. Our center is going to represent the value beta that best reflects the true population slope, and the standard deviation is the typical distance the response variable is from the expected value based on beta, or based on that particular slope. So both of these represent, A is just a normal probability plot of 1,000 simulated least squares regression lines, and B represents a histogram of the 1,000 sample regression line slopes from figure 12.4. The red density curve right here is for a normal distribution with a mean of 10.36 and a standard deviation of 1.27. So essentially all we're trying to get at here is that both of these images represent a whole lot of least square regression lines, or where their slopes were, essentially. The center of this is going to represent the actual slope itself of that population least squares regression line, whereas the spread is going to be represented by the standard deviation, which is 1.27, and the center is represented by the mean right here as well. So when we're thinking about how to describe a sampling distribution for slope, we want to let B be the slope. So again, let's say that we have our least squares regression line that's indicated like this. Okay, it's y, and that should be y hat is equal to alpha plus beta x. Okay, so let B be the slope of the sample regression line. The mean, or the center of the sampling distribution, is essentially just going to be whatever this B value is right here, this beta value is right there. That's going to represent the mean or the center of your sample regression line. The standard deviation is going to be a little different. So it is going to be basically the standard deviation divided by the standard deviation at x times the square root of n, as long as the 10% condition is met, where n is less than 10% of the total population. Now, you would have to be given the population standard deviation in order to solve for the actual spread itself. We'll go over, if you're not given that population standard deviation, we'll go over how to solve for that in just a minute. But that's essentially, you're taking the sample standard deviation divided by the population standard deviation times the square root of the total number in the sample, basically. And then when you're describing the shape of this distribution, the sampling distribution B will be approximately normal if the values of the response variable y follow a normal distribution for each value of the explanatory variable x. Okay, and kind of what that means basically is, if you're given a histogram like this, then you're good to go. All you got to do is just kind of draw your little line right here. Bell curve, excuse me, can't think of the word. Bell curve over your histogram right there, and if it kind of makes a normal shape, then you're good to go. However, if you're only given the line itself, kind of what this really means is that when you're thinking about normality, each one of these centers are going to represent a sample regression line, basically, okay? And so each one of these bell curves right here represents its own sample right here, and the one single line is representing the population regression line. Well, because each one of those centers falls on that line, what you need to know in order for this to be considered a normal distribution is that each one of those must have a standard deviation that's approximately the same width as the other sample standard deviation. So what that means is you can't have a curve that's like 20 times skinnier than this curve right here. They all kind of have to have the same equal distance right here in order for this to be considered normal. Okay, so that's essentially the goal, and you probably will not see a ton of this on the AP test. This is more for upper level statistics type classes, but that's just kind of what you need to understand, is that we're really looking for normality in the histogram as well as any sort of image that you see like this that might hint at normality for that population regression line as a whole. Now, let's look at checking conditions. Okay, and checking conditions is going to be semi-similar to what we've been looking at for the last few chapters, but it's actually going to add quite a bit more. And so really the acronym that we want to look at for this is, when we're asked to check conditions for a regression line, we think liner. Okay, so that's our acronym in order to check this. So first we want to check to see if it's linear. Okay, and linear is going to be the actual relationship between the response and explanatory must be linear. We can check a residual plot, and if it shows no clear pattern, then that relationship is going to be linear. Independent would be our next, the next part of our acronym, and that's essentially every check of independence that we've seen so far, and that's the individual observations must be independent of each other. When sampling without replacement, we must check the 10% condition. So our sample must be at less than 10% of the total population that it actually represents. Next, we want to check for normal, and so that's for any fixed value of x, the response value of y varies according to the normal distribution. And essentially what we're checking is the residual against the drop height in this case. And so really the normal condition is kind of, it's based off of this right here. And again, you can create a histogram based off of your regression line to see whether or not it's normal, and that's honestly what I would go with. But if you're not given that, then we'll go over kind of how to check for that as well. And then our fourth acronym, E, stands for equal standard deviations. And so that's the standard deviation of y is the same for all values of x, and here we're checking the residual against the z-score in this case. And then finally, our last acronym is going to be random, and that's, again, a very similar one that we've seen for the last few chapters now, and that's the data must come from a well-designed random sample or experiment. So how are we going to remember this? And that's essentially just linear. You can call it linear by including and right there, or you can just call it liner, one or the other. But you want to, that's, I think, the main point that AP really wants to drive home if they do ask any question along the lines of a regression line is when you're thinking about conditions, you think about linear, independent, normal, equal standard deviations, and random. Okay, so let's take a look at this example real quick. Mrs. Barrett's class did a variation of the helicopter experiment on page 738, and that helicopter experiment is this right here. Is there a linear relationship between the height from which a paper helicopter is released and the time it takes to hit the ground? So that's the experiment that they performed. Students randomly assigned 14 helicopters to each of the 5 drop heights, 152 centimeters, 203 centimeters, 254 centimeters, 307 centimeters, and 442 centimeters. Teams of students released the 70 helicopters in a predetermined random order and measured the flight times in seconds. The class used Minitab to carry out a least squares regression analysis for these data. A scatter plot and residual plot, plus a histogram and normal probability plot of the residuals are shown below. So you'll notice that this plot right here represents our scatter plot. This one represents our residual. This one represents our histogram, and this one represents our normal probability plot for all of that. So our problem here is that we want to check whether the conditions for performing inference about the regression model are met. We want to use our liner acronym. So first, we want to check to see whether or not it is linear, and that's we want to check the residual plot for that. And if it shows no clear pattern, then the relationship is linear. And so we can check this right here first. You notice that if I just draw a line straight through it, it's fairly linear, so we really can go ahead and just call that linear. You can also check this residual plot right here. Yes, this residual plot, and you'll notice that there's really no pattern as far as what you see here. In other words, like it's not like you have a bunch of data grouped here and then it kind of gets wider as you move to the right. That would show some kind of pattern. You really don't see much of a pattern at all within this residual plot. So that's two ways that you can check for linear form, but the scatter plot itself just shows a clear linear form as it is, so we really don't need to worry too much about that. The second test that we need to check is for independence, and what we can say here is that the helicopters were released in a random order and no helicopter was used twice, so the flight times are independent, basically. And then the third test that we need to check is for normal, and really, let's see. This is what you could say: the distribution of flight times varies normally about the regression line. I might even go further and include that when we're looking at our histogram right here, it kind of takes a normal shape of some kind. So, so that really honestly checks off our test for normal in this case. Our fourth test is the equal standard deviations, and so that's the standard deviation of y is the same for all values of x, and what we're really looking here is the residual plot shows a similar amount of observations above the regression line as below. So if we look at this residual plot right here, you'll notice that, and it's pretty hard to count because there was so many samples taken in this case and so much data, but what you're looking for is if there's the same number of dots above as there are below, then you pretty much have an equal standard deviation. And again, there's no pattern here, and as long as there's no pattern here, then you're probably going to be okay on that particular test as a whole. But you really want to check the residual plot in order to determine whether that test passes or fails. And then from there, the last test is our random test, and we just want to say that the helicopters were randomly assigned to their flight groups, and we're good with that. So that's all 4 of those tests taken. Now let's look at estimating our parameters. So if we want to solve for our least squares regression line in this case, again, that formula for that is y hat is equal to a plus bx. If you see it on the AP test, it might look something similar to this, where y hat is equal to b at 0 plus b at 1 times x. Really, if you can just convert that to what you know from this, then that's fine. But what we're looking for is where a is our kind of our y-intercept of this line, basically. And so that's the value of the response when the value of the explanatory is 0. So the value of our y-axis or our response variable where our explanatory or x value is 0 at this case. And then b is representing the slope or the regression slope. And so for every 1 unit change in the explanatory, the response value with b will change by b. Will change by b, sorry. That should say will. That's kind of confusing. So the response value will change by b. And then if we're going to solve for the standard deviations of the residuals, what we would do is we would say s is equal to the square root of epsilon of the residual squared. So we would take all of the values yi minus y hat at I, square that, add those together, and then divide by the total number in the sample minus 2. And the residual is the difference in the observations and the predicted value. And this is the typical distance a predicted value is from the true values observed.